Hey everyone, so how was your day? And did you like the previous video? So in this video, I have decided to make these videos, like more segmented and not like 1 hour long, but more like 15, 20, 25 minutes, like only this much long, like as short as possible and make them more segmented. So it's easier for everyone to watch and, like you don't have to go into like the video and go like, oh my God, I have to watch this 1 hour video. Because I know the attention span of our generation is like 5 minutes. And considering YouTube analytics, it's actually 1 minute, but yeah, whatever. So, yesterday we learned about Shockley equation, and today we'll do some questions on Shockley equation as written here. And we'll also study about the equivalent circuit model of diode and breakdown phenomenon. And that's about it. And then in the next video, we'll talk about Zener diode and the Zener diode's characteristics and all those things. So let me write this question real quick. So in this question, we have been given a silicon diode has a saturation current of 1 picoampere at 20 degrees Celsius. Okay. Now we have to determine diode bias voltage when diode current is 3 milliampere. Okay. Diode bias voltage is VD. Diode current is what? ID. Right? Yeah. And then we have to determine diode bias current, ID, when the temperature changes to 100 degrees Celsius for the same bias voltage, right? So nothing too hard. You have to remember a few key points, which basically are, give me a second, boom, 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 which basically are two equations. Let me remove this. Yeah. So which basically are two equations. You have to remember these two equations, which is first, I cannot, I'm sorry. So first one is Shockley equation, which is, if you remembered it, ID equal to I naught, which is saturation current, multiplied by the exponential of VD over eta, which is a constant. For silicon, it's 2. For germanium, it's 1. VT, voltage equivalent, or thermal voltage. Voltage equivalent in volts, -1. Right? And another, so with this we'll be able to find VT with the formula VT equal to T over 11600, right? And for the second, like with these two, we'll be able to find basically everything in the first question. And for the second part, we have to remember another equation that we studied about, which is I final is equal to I initial 0, 1 into 2 to the power T2 minus T1 over 10. So these are the three equations that you need to remember, right? And with remembering them, like I don't even know if you need to remember them because you'll be provided with a formula book in exams. But still, it's better to remember them because, well, come on, it's just three equations, right? So what do you have to do? For the first part, we have been given. So I'll write here answer. So we have been given diode current, which is ID equal to 3 milliamps, saturation current, which is 1 in 10 to the power minus 12 ampere, picoampere. Temperature is 20 degrees Celsius. You'll convert it to Kelvin, which then we'll get like 293 Kelvin, 273 plus 20. It's 273.15, but yeah, 273 is good enough. For silicon, we have eta equal to 2, right? Now, a diode equation is given. ID equal to I naught E Vd over eta Vt minus 1, right? And Vt equal to T over 11600. So we have been given T, so which is 293 over 11600, which would give us about 25.25 millivolts, right? Now, for the first part, A, the diode bias voltage, right? Vd. So for Vd, we have Vd here. We have been given Vd is here. We have been given Vt. We have been given eta. We have been given I naught. We have been given ID, diode current. We have been given saturation current. So we have everything in this equations, right? We just have to find this single variable. So what you do is you bring I naught here, then you add it plus 1, and then you take log and then multiply by eta Vt, and you'll get Vd, right? I'll show it right here. So not again. ID over I naught equal to e to the power Vd over eta Vt minus 1. Minus 1 goes there. ID over I naught plus 1 is equal to e to the power Vd over eta Vt. Take log both sides. We get log ID over I naught plus 1 equal to Vd over eta Vt. Now we get now we want to find Vd, right? So eta Vt log diode current over saturation current plus 1. So we have the equation for to find Vd equal to Vd. Right now we put in the values. 1, 2, 3, go. All right, sorry, my pencil died. So now we just need to put the values in this equation, and we'll be able to find the diode bias voltage. The values are 2 for eta for silicon multiplied by Vt, which we got 20, which we already got, which is 25.25 in 10 to the power minus 3 volts, log ID over I naught. ID we have 3 into 10 to the power minus 3 volt over 10 to the power minus 12, which was 1 picoampere plus 1. So use your calculators, and this value will come out to be 1.103 volt, which is our diode bias voltage, right? Now, for the B part of the question, where our temperature is increased to 100 degrees Celsius. So when temperature is increased, only saturation current changes. For saturation current, we have the equation I naught 2 equal to I naught 1 to the power T2 minus T1 over 10, which comes out to be I naught 2 is equal to 10 to the power minus 12 into 2 to the power 100 minus T2 minus T1. So T2 is 100, T1 is 20, which is 80 by 10, right? Comes out to be 10 to the power minus 12 multiplied by 2 to the power 8 is equal to 256 picoampere. To the power 8 is 256 picoampere. So we have the saturation current, right? Now, if you remember in the question, we were asked diode bias current, not saturation current, diode bias current. Now we need to put this saturation current we got back into the Shockley equation, which was, by now you should have remembered it, ID equal to I naught e to the power Vd over eta Vt minus 1, right? Now we put this saturation current into our Shockley equation, and we'll basically get ID equal to 256 in 10 to the power minus 12 multiplied by E, and VD was 1.103 for the same bias voltage. Remember, we have been given this in the question, divided by 2 into for eta, 32.5, 32.15 into 10 to the power minus 3 minus 1. Cool. Now you'll be asking where this 32.15 in 10 to the power minus 3 came from, right? Which is a good question. If you remember, VT also changes when with temperature, right? So for this we had to calculate VT as well, which would have been for, like, it's changed to 100, so 393 in Kelvin over, again, 11600 is equal to 32.15 millivolt, which is I have put in here. See, VT also changes. You have to remember these things. So this will come out to be 7.21 milliampere, 7.21 milliampere, and this is our answer, basically, right? So now that I've written the question, find the static and dynamic resistance of a PN junction germanium diode eta equal to 1 if the temperature is 27 degrees Celsius, converted to Kelvin, 300 Kelvin. And I naught is 1 microampere. I naught is saturation current for an applied forward bias voltage of 0.2 voltage. So it's easy. We'll find VT, we'll find ID, we'll use the static resistance formula of V over I. And for dynamic resistance, we have another formula, if you remember from previous class or previous video, eta VT over ID plus I naught. So let's do it. So answer for VT, we have T over 11600, which is equal to 300 over 11600, which we'll get 125.86 millivolt. For ID, you remember the formula. This is our saturation current, I naught exponential of VD, which is 0.2 divided by eta. For germanium, it's 1 multiplied by 25.86 into 10 to the power minus 3 minus 1. And when you compute this, we'll get 2.28 milliampere. Now for static resistance, is equal to V over I. We have been given V, we have been given I, 2.28 milliampere. This will come out to be 0.087 kilo ohm. Okay, or if you don't do the 0.087 kilo ohm, it'll come out to be 87.7 in your calculators. For dynamic resistance, our formula is eta VT over I naught plus ID. Remember this as well, quite important, which is 1 into 25.86 into 10 to the power minus 3 divided by 2.28 into 10 to the power minus 3 plus 10 to the power minus 6. When you compute this, you will get about 11.33 ohm. So static resistance for this diode is 0.087 kilo ohm if you use DC. So DC current, we use static resistance. For AC current, we use dynamic resistance. If we use AC, we'll get a resistance of 11.33 ohm.